Welcome to General Chemistry Mini Lecture Series, Lecture 50, Molecular Orbital Theory, the MO theory. Why do we need molecular orbital theory? You say the valence bond theory is pretty good, but the problem is some aspects of the bonding cannot be explained by the valence bond theory or by Lewis structures, valence shell electron pair repulsion theory, as well as the hybridization. Examples for the ones that cannot be explained by the theories we already learned so far are oxygen molecules, why it has a magnetic property, and also why some molecules are colored. To explain those, we will need the molecular orbital theory, MO theory. You may recall the Schrödinger equation. We learned that in previous lectures. In MO theory, we apply the Schrödinger's wave equation to molecules. When it comes to where we can find electrons or atoms, all electrons are found in atomic orbitals. And then in molecules, all electrons are found in molecular orbitals. You see, we have molecular orbitals versus atomic orbitals. In molecular orbital theory, the molecules are viewed as a collection of nuclei surrounded by delocalized molecular orbitals. Now let's take a look at the atomic wave function as well as molecular wave functions. So if we have two atomic wave functions, and when they reinforce each other, then a bonding molecular orbital is formed. You see the electron density, okay, is pretty high, and they exist between the two nuclei. So there's electron density right there. What does it mean? It means, electrons are found between the two nuclei, so that's why it is a bonding orbital. On the other hand, if two wave functions cancel each other, you don't have wave anymore. And then the electron density, there's no electron density. You see right here, there's no electron density between the two nuclei. Unlike here, you see, there's a pretty high electron density. So therefore, when wave functions cancel each other, it will result anti-bonding molecular orbitals. Now let's take a look at hydrogen molecule. Before hydrogen molecule is formed, you have two isolated hydrogen atoms. And this y-axis is the energy axis. Okay. So now, when we place the two isolated hydrogen atoms together, then here is the bonding molecular orbital. If the two wave functions cancel each other, this is the anti-bonding molecular orbital. You see there's no electron density here. The bonding molecular orbital is lower in energy than the anti-bonding. In addition to that, the energy in bonding molecular orbital is also lower than the energy in the atomic orbitals. You see, here the energy is higher, here the energy is lower. Just like filling the atomic orbitals, filling the molecular orbitals with electrons from low to high. Let's take a look at hydrogen molecule again. So in this column, that should be the molecular orbital of a hydrogen molecule, H2. And then in this column, that's the atomic orbital of one of the hydrogen atoms, isolated hydrogen atoms. On this side, the same thing, that's the atomic orbital of another isolated hydrogen atom. So both, basically, those are the two atomic orbitals. And now, when they form molecular orbital, you see, this is the bonding molecular orbital, that's sigma 1s, and then this one is sigma asterisk 1s. So this is the anti-bonding orbital. Initially, we have one valence electron in each of the isolated hydrogen atom, and now electrons will fill molecular orbitals from low level to high energy level. So therefore, we should have one here, then another one here, paired, which means with opposite spin. Total number of electrons should be 2, and now total number of electrons is 2. So therefore, nothing will occupy this anti-bonding molecular orbital. Let's bring up a new terminology, bond order. Bond order in molecular theory can be calculated using 1/2 of the bonding electrons subtracted by the anti-bonding electrons. Or I prefer to use this simplified equation, BO, bond order equals 1/2 B minus AB. B means bonding orbitals or bonding electrons, actually bonding electrons. AB is the anti-bonding electrons. Let's take a look at hydrogen. Okay, hydrogen, how many bonding electrons? 2. Anti-bonding electrons, 0. 2 minus 0 equals 2 times 1/2. Therefore, the bond order for hydrogen molecule, H2, is 1. Now let's take a look at helium positive. So it's an ion. Again, the center should be the molecular orbital for He2 plus, and then each helium atom should have 2 electrons in its 1s orbital. And then this is another helium, but since this one lost 1 electron, because right in the center we don't have a molecule, we actually have an ion. So we have to address that lost electron. So this one, helium, initially has 2 electrons, but now He positive should have only 1 electron because the other one is lost. And now let's take a look at the bonding orbitals, anti-bonding orbitals. And now we'll do the same thing, feeding the electrons into these molecular orbitals. So you see each orbital can accommodate a maximum of 2 electrons, 1, 2. And then the third one goes to there. A total of 3 electrons in atomic orbitals, and then 3 electrons in molecular orbitals. Now let's take a look at the bond order of He2 plus. The bond order, okay, 1/2 times bonding electrons, 2 bonding electrons, 2, and then 1 anti-bonding electrons, 1, then times 1/2. So the bond order is 1/2 for He2 plus. Now let's just take a look at helium-2, He2. Okay, so we'll do the same. The atomic orbitals, and then the molecular orbitals. Now let's fill the molecular orbitals. We have a total of 4 electrons in those atomic orbitals, and now we have 2 molecular orbitals. Each orbital can maximum accommodate 2. Then we will have 2 electrons in sigma 1s, the bonding orbital. Also 2 in the antibonding orbital, sigma asterisk 1s. Okay. Now let's take a look at the bond order using the same equation. So for H2, how many bonding electrons? 2. How many antibonding electrons? 2. 2 minus 2 equals 0. Therefore, the bond order is 0. Bond order 0, what does it mean? It means that bond does not exist. If that bond does not exist, then He2 molecule does not exist. That's why you never see He2. It should be always just He. This slide shows the molecular energy level for second period diatomic molecules. Do you guys still remember diatomic molecules? O2, F2, N2. So here has a Ne2, but it's just for discussion here. It actually does not exist. So with this slide, we are going to address mixing, 2s2p mixing. Without 2s2p mixing, as you can see, the order of energy level. So this is the energy level from low to high. You see the energy level from low to high is a sigma 2s, and now sigma asterisk 2s, then sigma 2p, followed by pi 2p. Let's concentrate on those two orbitals. Sigma 2p's energy is lower than pi 2p. In those molecules without 2s2p mixing, I will explain what it is. And now let's take a look at the other 3 diatomic molecules, B2, C2, and N2. For those, if you look at the order, after sigma 2s, it's not sigma 2p anymore, it's pi 2p. And then you have the sigma 2p. So therefore, if we concentrate just the sigma and pi, sigma 2p and pi 2p orbital, the ones without mixing, they follow the normal order. Now this is the normal order from sigma 2s, sigma asterisk 2s, sigma 2p, pi asterisk 2p, sigma asterisk 2p. So that's the normal order. And here, the order right here between sigma 2p and pi 2p is reversed. That's why we call this 2s2p mixing. That's with mixing, the order is reversed. Compare with the ones without 2s2p mixing, which follows the normal energy level order. This slide shows the same thing with the sp mixing. So you see, after N2, those are the normal order. Normal order, again, so you see that energy goes up. Normal order is sigma 2p lower than pi 2p. And then those are the ones with the sp mixing, the smaller ones. And then you see there pi 2p, this is the pi 2p. It's lower than sigma 2p. This is sigma 2p. So therefore, this slide also addresses the sp mixing, only from another angle. This is a summary slide. Again, we are talking about the sp mixing, and here use a different terminology called interaction. Large interaction means with sp mixing. Smaller interaction means without sp mixing. Those are the smaller ones with sp mixing. So everything shows here, all of those, they are the molecular orbitals. On the right-hand side, those are the diatomic molecules without sp mixing, or we call that with a small 2s2p interactions. Then their energy follows the normal order. Normal order means from sigma 2s sigma asterisk 2s, sigma 2p, then pi 2p. And on the left-hand side, as we already talked about, the ones with the sp mixing or with a large sp interaction, the energy level between pi 2p and sigma 2p, they are reversed. So pi 2p is lower than sigma 2p. Okay. And now look at this summary table here. The bond order, if you use the bond order equation, you can calculate. So for B2, the bond order is 1. For C2, the bond order is 2. And for N2, the bond order is 3. The greater the bond order, the more stable the molecule. So therefore, N2 is very stable than C2. And C2 is more stable than B2, okay? And look at here. This one, Ne2, the bond order is 0, which means it does not have any stability. That's why it does not exist, okay? So the higher the bond order, the more stable the molecules, and that translates that the higher the bond energy. You see, look at the second row, that's bond energy, with bond order of 1 in B2, let's say, it's 290 kilojoules per mole. With bond order of 2, that's 620, but in N2, bond order of 3, that's 941. And if you look at here, so that's a bond order of 2, 495. With bond order of 1, that's 155. The higher the bond order, the higher the bond energy or bond enthalpy. With 0 order, the enthalpy is 0. Nothing there. As we already learned, the bond length is related with bond energy. The lower the bond energy, the longer the bond. For this one, 290 bond energy, 290 kilojoules per mole, then the bond length is 1.59 angstrom. But when the bond energy is increased, then the bond length is decreased. If we take a look at the magnetic behavior, whenever you see unpaired electrons, then they are paramagnetic. So that's why B2 is paramagnetic. C2, there's no unpaired electrons. Does N2 have unpaired electrons? No. So therefore, both are diamagnetic. Oxygen is really the one I want to focus on. So from previous theory, whether you do Lewis structure, valence bond theory, we just never see single electrons in O2 molecules. But here, using the molecular orbital theory, we do see 2 unpaired electrons. And because of that, O2 is paramagnetic. Therefore, the molecular orbital theory does a great job in explaining why O2 is paramagnetic, while the other theories I just mentioned a while ago, Lewis structure, valence bond theory, and so on and so forth, they could not explain that. Again, this explains why the noble gases cannot form diatomic molecules because of the 0 bond order. I just commented in the previous slide that the molecular orbital theory is the only theory that can explain oxygen molecules' magnetic property. So the Lewis structure for diatomic molecule oxygen, so if you draw that now, you don't see any unpaired electrons. But the molecular diagram I already showed you, there are. And experimental results confirmed O2 has a short bond length and higher bond energy. That means you have a double bond in O2 molecule. And of course, using a molecular orbital theory, we can easily calculate the bond order for O2 molecule. That's 2. We already did that in the previous slide. That's it for lecture 50. I will see you guys in lecture 51, states of matter and gas pressure.